So I'm going to talk about what's new in Refinement and related tools. We've got a few key tools for Refinement with CCP4. These are developed in our group, the Motion group in the L&B in Cambridge. We've got VREF Mac, which is the main tool for Refinement, so that's the powerhouse. We've got Coot for visualization and model building and lots of other things surrounding that. Then we've got ProSMART for restraint generation and comparative structural analysis. LIBG for nucleic acid restraint generation, LORESTR, which is the automatic pipeline for low-resolution refinement, and AceDRG for ligand restraint dictionary and conformer generation. Now, I assume we know what refinement is. We've got a model. We want to refine the parameters of that model so it better fits our data. But in this talk, I'm going to talk about what's new in AceDRG, in the Monomer Library, in Coot, in LORESTR, Refinement with CCP4 and finally some new developments, new project on B-factor analysis. So to start off with, we've got ligand refinement. So geometric restraints for proteins and nucleic acids are pre-tabulated. These are distributed as part of the CCP4 Monomer Library. But ligands are more complicated, and we need a source of prior information to describe these to use in refinement. The commonly known structures are dealt with automatically. These are distributed as part of the monomer library. But if you've got a new ligand that hasn't been solved before, then you're going to need a description, a CIF file. And for that, we would use AceDRG. So what is AceDRG? Let's just have a recap. So the motivation is that the annex data do not inform about high resolution. They don't inform about bonds, atom assignments, but also the more complicated things. Hydrogen bonding capability, protonation of functional groups, torsion angles, chiral etc. We want to improve the quality of the prior information that is used during refinement. We want to generate restraints for ligands in macromolecular models, as well as for the macromolecules themselves. So the idea behind AceDRG is to rewrite the CCP4 Monomer Library in light of the hundreds of thousands of small molecule crystal structures that have been deposited in small molecule databases. These have all been obtained at much higher resolution and are not restrained in the same way as in macromolecular crystallography, and so they should be much more reliable. We can use information from these to generate details about the chemistry in our macromolecular models. The atom typing that has been traditionally used is relatively limited, so as part of doing this, we want to extend to encapsulate more information about the chemical environment. So at the minute, we're using the COD, which is a freely accessible small molecule database, but in principle, it could be using other small molecule databases such as the CSD. So briefly, what is AceDRG doing? Here we've got a hydrogen, and we describe this particular atom as a hydrogen which is next to a carbon, two hydrogens and an oxygen. Okay, that's quite straightforward in this case. Now let's consider what we've got for this particular carbon here. We've got a carbon which is part of two 5-member rings, a 6-member ring, whose neighbours are a carbon, a carbon, a carbon, and a hydrogen, and their neighbours are... It gets complicated, but fortunately we don't have to know about this. AceDRG does this automatically, is the point. We're encapsulating second and in some cases third order information in order to have a much more detailed description of the local environment. So bonded atom pairs are tabulated. We've got a hierarchical organisation of these, not only for bonds but also for angles and some torsions, etc. These are tabulated and are distributed as part of the CCP4 for quick lookup. This has been around now for a little while in CCP4. This is what you are using. What does AceDRG do? We've got a few functionalities. First, it's the restraint dictionary generator, so it will use these restraints that are distributed in order to generate new restraints for your ligands. So that will be where your CIF file comes from. It will also do conformer generation, so it will generate coordinates from a graph-based molecular description, refine that conformation using VREF Mac 5, and then give you a PDB file with starting coordinates. It's not necessarily going to be the conformer in your particular case, but it is going to be a good starting point. And the new feature is link creation. So links are something that we've been able to do. We can either create a link record manually and put it in a PDB file. We can use Coot to click onto atoms to create a link. We can use JLigand to create a link. All of those use the kind of an old simplistic description, whereas now in AceDRG, when creating the links, it will use this more complete, more detailed description of the chemical environment, so hopefully it will be much more reliable. This is now available. So when ligand fitting in CCP4, the general procedure is that if you've got a common ligand, you know the three-letter code, therefore it will just work. It's in the CCP4 Monomer Library, you haven't got a problem. You haven't got to think about it. However, if you've got a new ligand, you need to take your smile string, then maybe use AceDRG or JLigand or Lydia in order to create a restraint dictionary, your CIF file, and some initial coordinates, that's your PDB file. Then you would use Coot to find the position and pose and fit the density, fit into the density and do local refinement before then doing full refinement with VREF Mac 5. And this can all be coordinated via the CCP4i2 interface using the make ligand task. That is your starting point if you're trying to fit a ligand. But that's been around for a couple of years. Now what is new? What is new is the CCP4 VREF Mac Monomer Library update. So we wanted to extend the Monomer Library, want to automatically update the Monomer Library in light of these developments in AceDRG. We can't include all ligands. I mean, the potential number of ligand chemistries out there is huge. That would not be tractable. So instead we use a sensible subset of the possible ligands. For that we take the CCD, the Chemical Component Dictionary, from the PDB. We only consider valid non-polymers. Certainly the amino acids and nucleic acids, because they're so important, are considered separately, manually. And we're only able to consider the extended organic set. General metals are not included because they can't be dealt with by AceDRG at the minute, although hopefully in the future that will be resolved. So last March, using AceDRG version 190, we did this initial update. 2.2 thousand entries were added and 3.7 entries were replaced in the Monomer Library, followed by a much more comprehensive update in September, where an additional 8.8 thousand entries were added and 7.4 entries replaced, resulting in over 24,000 entries now in the Monomer Library, which should make it much more easy if you are dealing with a ligand that is already known. Future updates will continue periodically along with the expansion of the CCD. I should give a shout out for Martin Voda, who's been useful. Generally was useful for validation of output CIF files from AceDRG for this purpose. I mentioned that links is a new feature, so covalent links in AceDRG. AceDRG requires a link instruction file in order to work with this. So suppose you've got a cysteine and you want the SG in that cysteine to be linked to the C1 in some custom ligand that you've got called TMP. Because cysteine is a standard residue, you don't need a CIF file, but because you've got a custom ligand to link it to, you provide the CIF file corresponding to that ligand. You create your instruction file, pass it to AceDRG, and a new link dictionary with possible modifications are created. So in this case, we've got our cysteine. We want the SG to be linked to the C1 in monomer TIMP, in which case AceDRG will create a description for this combined linked molecule, along with a single bond by default. Indeed, if you wanted a double bond, you can change the bond order of the link, you can change the bond order of adjacent bonds, and also you can delete non-hydrogen atoms from either compound, noting that the hydrogen atoms are added or deleted automatically so as to make sensible chemistry. So these AceDRG links can actually be automatically created in Coot. So if you go into the extensions menu, modules, click on CCP4, you will get a new tab pop up at the top. And you'll see that there is a make link using AceDRG option, in which case you can click on two atoms and hopefully it will just automatically create this link record for you, and then that should propagate through your jobs. And so let's move on now to what else is new in Coot. And this is all down to Paul Emsley, who should be credited for all of this. New Ramachandran plots. So here's the old ones that we're familiar with looking at. More recently, in the current CCP4, we've got plots that look a bit like this, looks a bit nicer. And in experimental Coot, they look a bit more like this, so improvements again. Not only do they look nicer, the underlying data is different. So it's been quite a long time since the data underlying the Ramachandran plot's been updated, but pretty recently it has been updated by data mining the PDB. That should propagate to other non-Coot programs also in the near future. What else is new in Coot? The automatic residue reorientation. So, you know when you click on next residue, you'd space, 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 and it translates along the chain? Well, now as well as translating, it's rotating for you, so that you are always going to be having a look at the same view relative to that. So you can see the side chain, you're not losing bits of density. It's pretty useful, much more intuitive. You can see what's going on, and it should make your life a bit faster. At least I think it's quite nice. However, if you get tired with the actual rolling, but you still want to reorient, you can instead change it to snap mode, in which case it will still focus in on the same view of the residue. So you're still looking at the side chain in each case here, making it very quick and easy to see when something needs to be changed. It should help to improve productivity with a bit of luck. Yeah, sure enough, we can see that something needs to be added there. Okay. What else is new? We've got non-bonded contacts in real space refinement. So here, if you were trying to refine a particular lysine that's not in the correct place, previously it would get sucked into the wrong density. If it's near another bit of the protein, it could just fall into this region here. But now we've got non-bonded contacts from the environment residues, which should stop that happening, and instead, so it will bounce the lysine side chain away from other bits that are modelled, so that it should fit into the density that it belongs in. Also, Coote VR from Hamish aims to offer all of the features of Coot, but with the benefits of a VR interface. So it should have more articulation. So you can see Hamish down there with his headset on. He's got his two hand controllers and is able to interact directly with Coot from that. There should be greater visual clarity because you've got you're looking at it in 3D. You've got better depth of field, and there should be 10 times more screen space. And so you don't need these drop-down menus. Instead, you've got the different buttons around the side of the screen. It's a completely different way of working in Coot. If you're interested in that, Hamish is hanging around just outside the lunch hall, and also he's doing a lunchtime bite session tomorrow if you want to have a chat. We've got loops for missing residues. So if there are particular regions in your model that are missing, you can now see these dotted chains so that you can see which bits of built chain should be linked together eventually. We've also got multi-level blurring and sharpening. So in the extensions menu, or the calculate menu in the new experimental version, if you go into modules and then cryo-EM module, although I don't think you specifically need to be working with cryo-EM structure, you can have this multi-sharpen option, in which case it will use VREF Mac, not Coot, for the sharpening and blurring. You can specify how many levels of sharpening and blurring you want, and what the B factor range should be that you're sharpening and blurring by, in which case you'll be able to view a multiple maps at once with different levels of sharpening and blurring, which really can help to improve interpretation for both low-resolution MX and high-resolution cryo-EM map interpretation. Finally, we've got multi-threaded refinement using ProSMART restraints. And so here's we're trying to refine this big region here. It's now computationally tractable due to the multi-threading that's been put into Coot. If you try to do that, as you can see, it's just creating nonsense. It's just falling into the density. You need something to stabilise that, and so ProSMART restraints are one way to do that. So if you go to the ProSMART menu, we're going to be generating some restraints, and here you can see a representation of all of these interatomic distance restraints that have been generated. Let's undisplay those and instead go to refine them. We're setting a particular German-McClure parameter value that's controlling robustness to outliers. You can try different values to see what works for your particular case, which now when we try to refine the structure, it holds together an awful lot better. There's still a lot of flexibility. It's restraints, not constraints, but the model should refine a bit more sensibly. As you can see here, the radius of convergence is much bigger. There we go, pop into the density, and now the side chains can just sink into where they belong. So this is quite a nice tool that can help if you're relatively close to where you want to end up, but you just need the model to sink into the density. Let's move on now to LORESTR. Just a recap of what LORESTR is. The idea is that the efficiency of ProSMART generated restraints greatly depends on the homologs that are used. Indeed, if several homologs are available, then substantial manual effort can be required in order to get a reasonable protocol and end up with a decent refinement plan. There are other refinement parameters that also need to be optimized in this sort of case, control and scaling, solvents, etc. The solution for this is LORESTR, the Low Resolution Structure Refinement Pipeline. You would take input, target, and model and data. It will analyze this input data and determine appropriate twinning, scaling, and solvent parameters. Then you can provide your own homologs, but it can also do a blast search using your sequence, analyze homologs, and rank them to determine what sort of protocols should be generated. It will then use ProSMART to generate restraints using these homologs and run all of these different refinements in parallel for you. It will then analyze the results, decide which model is the best, give you scripts for ProSMART and VREF Mac, and report on the output. In the tests, R factors were improved for 98 out of 104 low-resolution test cases. That's quite a lot. It should be taken with a pinch of salt. Of course, they're taken from cases from the PDB already. The point is it can make your life easy. It's not necessarily going to solve everything for you, but it is going to give you a good starting point. And so for the sake of one automated runner button, it can help you to start knowing what might be a reasonable refinement protocol for your low-resolution case. In terms of what's new, LORESTR is now using LIBG to generate nucleic acid restraints. So we've got base pair restraints to hold the bases together, and the base stacking restraints to ensure that they are suitably parallel. So LORESTR will try using that as part of its generation of protocols. LORESTR is available in CCP4 as well as in CCP4 Cloud, as Billy was mentioning earlier. You can see down here in the refinement tab, we've got the low-resolution refinement pipeline. And this is what the interface looks like. You provide your input model and data, provide any homologs that you may have, which may be your own that aren't published, or it can just do a blast search and it will do it for you automatically. In terms of reporting output, it will give you a list of all of the protocols, along with output R factors and geometry statistics for mole probability. It will decide what it thinks is probably the best solution, but that's not always the one. You might be interested in having a look at the different protocols, in which case you can have a look at here, for example, the mole probability score versus R3 to help you decide which protocols might be reasonable and which might not. In terms of the refinement interface in CCP4 perhaps one notable change that's happened recently is support for Electron Neutron diffraction experiments. So here on the Advanced tab, we've got diffraction experiment type. We can choose between X-ray, electron, and neutron. If we've got electron, then we can choose which form factor calculation to use. That's hopefully going to be useful. Also available soon, we should have a new dictionary accumulator which has been generated, which has been created recently for if you've got multiple ligands in your structures, you may have multiple links and modifications, and all of that needs to be combined. We've got a new dictionary accumulator to do that, to replace libcheck. It should be more deal with a large number of cases. Again, a shout out to Martin Voida. Gemmy was used for SIF passing in this case, and he's been useful with support. We expect there to be a dedicated CCP4 I2 interface for creating links in the near future. And also the validation task has been chained onto the refinement pipeline. So shout out to John Aguirre here, who has created the CCP4 I2 validation task, which gives you mole probability analysis, average B factor analysis, and Ramachandran plots, and no doubt other things in the future. All of this output, as well as being a part of the dedicated validation task, is chained onto the refinement task, and that should be released in an update in the very near future. Finally, a little project, very interesting and exciting project that's been done by Rafiga from Azerbaijan, based on the idea that B factors should obey shifted inverse gamma distribution. So here's a shifted inverse gamma distribution, here's the formula for it, and you can see that there is an alpha parameter and a beta parameter. Now, if you plot the alpha parameter versus beta parameter for 4,000 to 6,000 models from the PDB with reasonable resolutions, then you get a very tight distribution of alpha-beta parameters. That information can be used to assess whether your model has got something wrong with it, essentially, as well as other things. Here's a particular example where in a model 2BP7 that was deposited in the PDB has got a very unusual distribution. It doesn't really fit the inverse gamma. For sure, alpha and beta parameters, when estimated, are way outside of the normal range. And you can see that in this ligand region, actually, it's been filled with waters instead of being modelled as a ligand. If instead you put the ligand in and refine it without really trying to do too much else, the distribution gets much better and the alpha-beta parameters get a bit closer to what they should be. The point is that you can look for abnormalities, identify problems, just based on having a look at these sorts of properties. This is just one particular application. There is extended scope, and hopefully this sort of analysis will show up in the interfaces in the very near future. So what's new in VREF Mac 5? I think from a user, there's been all sorts of things under the hood, but from a user perspective, perhaps the most interesting thing over the last year is the substantial speed up of maybe 2 to 3 times, so it's much, much faster than it was a year ago. And this is mainly from improvements in scaling and map gradient calculation, as Garib Meshadov, who is the principal author of VREF Mac. Prospects for the not-too-distant future, we got migration to GEMI for input and output in VREF Mac. So that's for reading and writing MMSIF files. In particular, it's already been implemented, but it's entering the testing phase. Hopefully that will be done relatively soon. And there's lots going on in terms of macromolecular refinement against cryo-EM reconstructions. In the near future, we hope to see difference maps for cryo-EM, as well as updated maps after refinement, which is currently not done at the minute. The map remains the same before and after refinement. And that brings me to a close. So here's our group up here, and here's here's who's in it. I've talked about Faye's AceDRG, Oleg's LORESTR, Garib's VREF Mac, and Paul's Coot today. Also mentioned Hamish, Marcin, Rafiga, John. Also a shout out to Martin Noble and Stuart Nicholls for help with CCP4 related things. The CCP4 core team, our colleagues and users for feedback. Here's some references to those pieces of software. And of course, all of the developments that we're seeing in R2 will no doubt make their way through to the CCP4 Cloud too. So that's an interesting and exciting development as well. Thank you for listening. Has anyone got any questions?